Okay. Okay. Hi, everyone. Hello. So I think everyone's done the lab for yesterday and the day before. So hopefully things will make more sense during today's lecture. Today is essentially going to be the last lecture where we are basically focusing on just this kind of micro rules for how C is written. We'll move on to more higher level, just like implementing algorithms and stuff next time. Hopefully in the lab, I don't feel like you could tell someone like the 20 syntax rules and have them actually apply them right away in the lab. But if you just work from examples, I think it worked out for most of the people in the lab. There's going to be more exercises. I should say, I am sorry if I haven't replied to your email in the last couple of days. I will really try to get on top of things and post everything ASAP. I've been having some issues, but hopefully we'll be able to resolve that. Okay, so here's basically still the story for the first half of this lecture. This is the syntax rules for C. So we added one more at the end of last lecture, which was that if you have an array like this, when you actually use the identifier R, so when you just type in R, except in one particular situation, which we'll talk about later today, it's the same as just saying the address of the first element, right? So the way arrays and the way strings are represented, more or less, there is like one tiny difference, which we'll talk about. Basically, we're talking about the address of the first element in the block of elements. Okay, and that's the same as what we had before. So we'll refer to those as well. So I want to talk again briefly about how strings work in C. And the answer is C does not have strings. C has arrays of characters that you might like to interpret as strings, right? So the difference is that this syntax, you can use it when initializing, but what it means is you are declaring an array of type car. So you have, in this case, at least 4 cars here. The 4 cars are, so car for character, are A, B, C, and then there is a null at the end to indicate that that's the end of the string. So this is what this thing means. So it looks like you're declaring a string in Python. Really what you're doing is you are declaring an array of characters. This looks almost the same, and this would compile, but this has an issue which we'll discuss momentarily. So it does this. So this is more like what you have in Python, where you're saying S2 is going to represent the thing that's kind of like a string, right? And then put ABC somewhere in memory. So the difference between put ABC somewhere in memory, that's what we do in Python. Here we're saying I have this array S1 and I want A, B, C, and null in this array. Does that make sense? So let's maybe do it in Python Tutor just to see the picture. Here did this, so need to fix this to be straight. Okay. So here you see the difference between how S1 is represented and how S2 is represented. So S1 here is an array, so 4 slots. Each slot has a car in it. S2 is one address. When this line is run, in this case, Python tutor says, okay, so I decided that ABC lives, somewhere over here. So somewhere over here, you got to scroll to see it, right? And it's like somewhere. In the same way that you would have a memory table where you would put a string in Python. This is not really somewhere. You can actually go to S1 at 0 in the same way that you can go to S2 at 0, but you can modify S1 at 0. And we'll see why in a second. So the shorthand is that this is actually immutable in the same way that a Python string is immutable. Okay. So the actual type of ABC when assigned to S2, so the type when this is happening is actually not car star, it's const car star. Okay, so what const car star means is it's an address of a block of values, the contents of which you're not allowed to modify. Okay, so what happens here is you might get a warning if you do this. We'll compile it in VS Code in a second, and we'll see the warning. And what's going to happen is here you're basically forcing what really is a const car star, so the kind of thing whose contents you're not allowed to modify. You are what's called casting it, converting it to car star, the kind of thing that looks like you could modify its contents. And what that can do is it can just lead to your code crashing. So let's try this. Wait, didn't I? Yeah, I did. Yeah. Okay, so just to repeat the process, so I'm doing a new file. I'm putting it in the main function. Doing it like this. Fixing this to be single quotes. Fixing this to be actual text quotes rather than PowerPoint quotes. Return 0 doesn't have to be. Okay. I said Control S. I'll save it here to leg 2, whatever. and I'll save it as a .c. So this is just deciding where my program is going to live. I will then, you don't have to, but it resolves a lot of problems if you do. I will open this file, this folder where my program is. So I'm opening the folder. So now what happens is my file is over here, and I can try to run it. Yes. There we go. So the first time I run it, it's going to prompt me to select the compiler. On ECF, that should be fine. So on your own machine, select the one that's GCC. If you don't have GCC, you can try other stuff, but probably you need to figure out a way to find GCC. We'll have support for that later on in the week. And what happened is the program crashed. Okay, so the reason the program crashed is again, you're not actually allowed to modify the contents of So to be clear, what do I mean by contents of a const car star is go to address S and modify the contents there. Right? So this is what's called undefined behavior. So essentially, C allows you to a much greater extent to break the rules than Python does. If you break the rules, like for example, you have something that's really const car, but you implicitly converted it to car star, and then you try to modify the contents. According to the C programming language specification, that's undefined behavior, which means that C gets to do whatever the hell it wants, including just crashing, which is what it usually wants to do. You'll find. So worse than that, sometimes it won't crash, even though there is a bug. So that means that eventually you'll find out when it crashes on a different input, but it's not guaranteed to crash every time. Okay, so that's const star. And here, so what we did is like we implicitly converted const car star to just the car star. So S1 is of type car star, which means that C is going to be fine with you trying to modify it. It's just that it's going to crush during runtime. So you can protect yourself by matching the consts. So if you say const car star S2 is equal to ABC, that's allowed too. So that means that S2 is this too small, or is that okay for the font size? People in the back? Okay. So in this case, S2, it's the address of the A, and not allowed to modify contents at S2, and here meaning the program won't compile. So if I try to do the same thing here, so S2 at 0 is equal to Z or something, and I try to run it, what's going to happen is And by the way, in this case, you should say abort because debug anyway just means that you're taking whatever old version of the program you had, not the new one, which didn't compile. There is no program that's compiled right now because there is an error. So we just say abort. And what it says is this is just a compilation error. You're not allowed, and it underlined it here as well. You're just outright not allowed to do S2 at 0 equals something. Yeah.
If without the constant keyword, you cannot modify the string anyway, then how do you modify the string?
So you cannot. So if you create a string, so the question was, how do you modify the string? And the answer is, if this is how you created it, you cannot. So it's create, and there's going to be a slide about why, but you created it as a const char, just like in Python, you create a string, you cannot modify it. Here, you cannot modify it. You can, just like in Python, say something like, S2 is equal to ZBC or something instead, right? So that's completely fine. So that's completely fine because this is not changing the contents, but rather just changing S2. Okay, so this is what you would do in Python, right? If you want the same variable to refer to a new string in Python, that's what you would do, is you would just say, equals to something new. Yeah.
So for the first example, the difference is like you declare it as like car star, which technically means it's const car star, but it converts it to car star.
This is const car star, but then S1 is car star, and C allows you to implicitly assign something that's really const car star, so something that you're not supposed to be modifying, to a car star, which you are allowed to modify, so it won't catch the issue during compilation.
So, okay, so there won't be an issue during compilation, but when we try to run it, there could be, like, it could crash.
Yeah, it could, well, it could crash, or like it can, so undefined behavior really means undefined behavior. It could do anything. It could just like silently change your string to something else in principle if it chose to.
So ABC itself is a const car.
That's right. All right, questions about this? Yeah. So const car, sorry, and you said const car, really const car star. So const car star means, so it's a type of a value. So in this case, S2 is a value of type const car star. So it's an address of a character somewhere in memory. And additionally, you're constrained from trying to modify the contents of the memory block to which it refers. Okay, and the mechanisms in terms of how you're constrained are, if you try to modify something like S2, then it just won't compile, so it won't even do it. If you implicitly convert between what's a const car star to just a car star, C is going to allow it. However, then trying to change the contents of S1 is undefined behavior. Yeah.
Like, you said S1 was pointer, like what does, like, if you want to say what S1 practice doing?
Intuitively, S1 is the address of the A. So this is the picture over here, right? So this is this, right? And here we have the address where the A is. So this is this address. And then it's a string in the sense that eventually you're going to encounter a null if you try to go through this string.
Well, what does like the bracket do?
The bracket, this one?
If yes, only added like bracket.
Oh, this is just do you mean this one? Oh, this just means I want to access the first element, right? Because it's a block of cars, just like you can have a block of ints. Yeah, yeah. So that's not exactly precise the premise of the question, right? So car star allow you to modify the contents. So what's also true is if you convert a const car star, so this is a const car star, if you convert it to a car star and then try to modify the contents, it will crash, usually. So on the other hand, here it won't compile, but there are ways of having those kinds of things where you are allowed to modify the contents. We in fact saw examples. So if you look back in the slides, we could have things like this, for example. So that's kind of the simplest example. Yeah, that's a good one. Completely allowed. So that's same as right. So this is now not a valid string, but there is also ways to make them valid strings. So that's completely allowed. In addition, and I'm sorry this is complicated, but this is what it is. It's going to get, I mean, it's not going to get much more complicated throughout the semester, so you'll just get used to it. In addition, we had the issue of this guy, which looks like this, but isn't. So this guy is an array of cars, right? And you're completely allowed to treat it the way you would treat an array. So S1 at 0 equals something new, completely fine. Now, this doesn't look like it's car star S1, but we'll see, we saw last time and we'll see today as well, that actually it gets converted to a pointer to a car. Okay. So we'll summarize the string stuff later on as well, but for now, just know that those things are all out there. Yes.
So the above one is mutable, but the one below is immutable.
Yeah. Really it's this one that's mutable. So the difference technically would be that this is not real. So this is just a way to initialize an array in a convenient way. Here we are actually saying S2 is the address where ABC lives. Okay. So the way the memory allocation works is the second line, that's exactly as in Python. So you put ABC null somewhere in memory, and then you record the address of the A. Okay, so this is this line. This is quite different. This is saying S1, we have a slot for S1 where we have enough space to store 4 elements, and then we're initializing it with ABC. So this ABC, it's not a real string literal, if you like. So we're not assigning ABC to S1, we're assigning A to S10 and B to S11 and C to S12 and now to S13, as opposed to actually putting all of this in memory and then just putting the address where the A is over here. Yeah.
What's the advantage of using the first method?
The question was, what's the advantage of using the first method? Well, for one, if you're interested in being able to change your string during the program, that's one way to do it. Another issue is, another advantage is in terms of memory management, and that would have to wait. Yeah.
So why, I don't know if you explained this one array, why is the one array mutable and the other one isn't, even though they're both arrays?
So, okay, so I'll just say it one more time and then maybe we'll move on. It's a little bit like that in the beginning of 190, unfortunately, where we got to start somewhere. And I want to tell you, like, technically the minimum amount of rules that you need in order to proceed, and then we'll kind of fill it out. But again, so what's happening here is the same thing as in Python. So this ABC goes somewhere in the memory table. So heap in C terminology, that's the memory table. And then we assign the address of the A, so this guy, to S2. Okay, so that's what's going on here. What's going on here is we're saying I'm having an array of cars. So that's the left-hand side. And then this looks like you're creating a string ABC, but you're not. Actually, this is just equivalent to, and we said it last time as well, or it was in the slides, I guess. So this is equivalent to doing this, right? So we're not really creating a string somewhere in memory. We're just declaring an array, and then we're initializing it using the shorthand notation. Yeah.
Sorry, last question. The top one is mutable, correct?
S1 is an array. You can change elements of the array. Yes.
S2 is not, though.
So you cannot change. So the right-hand side is not mutable. Yeah. So mutability is a Python concept. So here, what you would say is the right-hand side is a const char star. You're not allowed to change its contents. And if you kept it as a const char star, you would not be allowed to change it. It would just not compile. However, in this case, we did change it to a char star, which is common practice, in which case trying to change a char star, which was actually converted from a const char star, is undefined behavior. All right. All right. So, okay. So that's const char. So this is mostly where you would see this kind of thing. You can also have just consts that are ints and chars and stuff like that. So those are just variables whose values you cannot modify because the compiler will yell at you, right? So if you try to do like constant A equals 42, and then you say, oh, I want A to be 43, that will just produce a compilation error. And similarly for char. Okay. So the difference is what we've seen over here, right? So you are allowed to do this to a const char star S2, right? So const char star S2 means that you're not supposed to modify the contents, right? So this is not allowed. But you are allowed to modify the variable itself. Make sense? So that's const char star. On the other hand, this is just, you're not allowed to modify the variable itself. You try it, that's a compilation error. You might reasonably ask, well, what if I want to ban the modification of the variable itself? Totally. That works like this. So it's char star const. That's what it means. Okay, so here you are not allowed to say str is something new. That produces an error. You are, however, allowed to go and modify the contents of str. Make sense? So another thing that you can do is you can ban kind of both going to the address in the memory table and changing stuff there and changing the variable itself. So in this case, str equals world is not allowed because it's like const char star const, right? And this is also not allowed. Okay. So to summarize, unless star const type just means you're not allowed to change the value of the variable, the compiler will yell at you that you're trying to change a constant variable. With pointers, const char star or const int star means you're not allowed to modify the contents. Char star const means you're not allowed to modify the address itself. and you can combine them. You can say there's a const here and a const here, and that means that both this and this is banned. All right. So one more thing that had to go somewhere, you can never actually reassign arrays. So here S is an array, cannot reassign it, cannot reassign an array of ints or of anything else either. That would just be a compilation error. All right, questions about this? So what's the point of all this? Seems boring and annoying. And it is to some extent. So const correctness refers to this idea of keeping track of what's const and what's not, and inserting consts when you think is appropriate. It's kind of like less shooting yourself in the foot. If you know that some data is not supposed to be modified, and if it is modified in the code, that's because of a typo or a bug or some kind of error that's not supposed to be there, you want for the compiler to yell at you if you try to do it, right? So it's like you're constraining yourself from doing something that you know you're not supposed to do. So that's kind of the point. Another point of, like, you could say, well, like, why do that? That's adding extra work. Is if you're adding extra work up front, even if it's not for catching errors because you think you won't commit errors, maybe the reason you won't commit errors is because you need to make a mental note of, okay, I'm not supposed to be modifying this variable. If I'm modifying this variable, that's bad. And maybe just this process of thinking helps you write less a code that's less buggy. Okay. So another just like historical note. Why is it that string literals are constant? So when I'm talking about string literals, I'm referring to this kind of deal. So why is it that this must be a constant? It doesn't have to be, right? And the reason it's kind of partly historical, partly it still works better that way. So data on especially older computers, now on kind of edge devices as well, where things are more difficult in terms of the amount of memory that you can afford. Data was stored in read-only memory all the time, right? So read-only memory would be data that you can access, but to which you cannot write. So an example of something that's like read-only is like this punch card over there, where data would be encoded in terms of the patterns of the holes that would be punched into the punch card. And if the process for compiling, which like that was not like fanciful, that could happen. If your compiler actually compiled the code into punch cards, then it would be advantageous to have all the string literals that are already literally in your code be in the read-only memory, so be represented as hole in the punch card, rather than something that's slower to access and more expensive, like the magnetic tapes over here. So the magnetic tapes, and how many people have like you probably grew up after VCRs and stuff, right? But that's like that technology. With kind of magnetic tape. So that is read and write, but that's more expensive and it's slow. So here, how many people have seen like something like that, like a VCR cassette? So not everyone. Anyway, so there is a roll of tape in there. And then if you're using it to watch a movie or listen to music, that's fine because the tape rolls and the head that's reading off the data is just like reading exactly the right data. But if you're using it for computer memory and you need to look up something at address 1000, and then you need to look at something up at address 5000, well, you need to like fast forward or rewind in order to actually get at the data that you want. Yes.
The last point there, it says write only. Does it mean read only, or is that meant to say write only?
So it's I mean, this is well, write only is kind of meaningless because what you're gonna do if you just write and kind of treat. I think I actually did mean write only in the sense that like when you're I meant read only, but like yeah, like punch cards could be in write only format in the sense that the machine that like makes the holes is not necessarily able to read. That's a different machine that would read. Yeah. So all right. Cool. And you know, there were compilers that would compile code to kind of those patterns on punch cards. And yeah, like it just makes sense to write something like that there. In modern times, don't really compile code onto punch cards very much anymore. However, one advantage of having strings be constant is that the same thing that we saw in Python, right? So if you say car S3 is also ZBC or something, right? Then there is no point to storing ZBC twice in the code if you know that those strings are constant. Does that make sense? Because essentially what the compiler will do is it'll say, oh, like we've used like this ZBC already, and this is a constant anyway. So quite likely S2 and S3 here would actually be the same address. So so S2 and S3 would be aliases. Let's see if they are over here. It might or might not work. That would be different on different computers. So I'll print the actual addresses. I'll explain the %LD in a second. Right now, I'm just printing them. So I'm printing S2 and I'm printing S3. So this is kind of equivalent to Python ID. Yeah. Right. And indeed, okay, I didn't need the comma, but as you see, those addresses do happen to be the same. Didn't have to be the same, but they turned out to be the same. And the reason there is a space here is I would also like to use this opportunity to go to the prompts. So here it compiled, so there weren't kind of crucial issues, but it isn't happy about the %LD. I'll explain why in a second, but it's printed. So warnings can sometimes be fine. All right. Questions about this? So we saw this in Python as well, right? Where sometimes Python would reuse the same string multiple times in the same location for different variables because it knew that the string is immutable. So there's not an issue with aliasing. Yeah. Can you change S3? No. So S3 is exact. So again, depends what you mean by change, right? So I can say S3 is equal to something else now. I cannot say, so this is fine. I cannot say S3 equals X because that's undefined behavior. Right? Okay. So yeah, so that's kind of one of the famous quotes about kind of all of this. So C makes it easy to shoot yourself in the foot. So for example, by doing something that's actually undefined behavior. So this is more about C++. So you need to learn a little bit more to really get this joke. But C++ makes it harder. But when you do, it blows your whole leg off. So Python only on the other hand, it's just like a toy gun. So yeah. So okay. Anyways. So summary again. Nothing really new, but I want to do a few exercises now after the summary. So go here, please. So we are ready to do Q1 through Q10. But I'll give you a few minutes to kind of think about it, and then I'll do a few of them. And technically there are solutions, but no peeking. I'm very proud of the buttons. I would say I made it myself, but actually it was ChatGPT. I like the buttons. Yeah. There, and it's linked from this slide. Yeah. All right, so let me do a few, and then I wanted to do one more slide as well. So this is nothing. So integer variable a, initialize it to 42. So that's, again, any variable in C, you have to say what the type is. Optionally, you can initialize it like so. So a pointer to an integer variable, a PA, so pointer to an integer is int star. PA would be just the name. And we want to initialize it to the address of A. So again, kind of, especially at first when you're doing those exercises, just, look at the summary. It has everything that you need to do. It's just about figuring out how to combine those. So here, there is the type int star, and address of A is address of A. You need to remember that the right-hand side needs to match the left-hand side. So here, the left-hand side is of type int star, and the right-hand side is an address of an integer because A is an integer. So they're both int star. So that's good. So using PA without directly using A, change the value of A to 43. So how do we do that? So PA is the address of A. So to go to the address, to the value at the address, you say star PA, right? So very important note that this is int star, this is one single unit, and that's a type. the star here, it's related but different, right? So the star here says, go to this address, right? So people usually get confused, but maybe it's just inherently confusing, and it's unfortunate that this star here and this star here are related but not the same, but they're not, right? So this is just one unit in star, right? And here we're saying star PA is equal to 43. Change the value of the pointer PA to something else. And we want to make sure that the value A doesn't change. So the easiest thing to change PA to is just 0. You could try to make up, like other values that will give you at the very least a warning, because it's probably not a valid address. You could also imagine saying something like, int B and then PA is address of B. So the thing to notice here is the difference between this, and both are allowed, right? So let's visualize the execution here. So show memory addresses. So here we have the slot A, the slot PA. They are both data. It's just that PA happens to be an address. And here, when we say star PA equals 43, that means go to this slot, meaning over here, and set it to 43. So what's going to happen is this becomes 43. This means, just like this means put 42 in A, this means put 0 in PA. So what's going to happen here is PA is going to become 0. Okay. Note that A did not care. So again, think of the analogy of like you have my office number on kind of on a post-it note. Just you write something else on the post-it note does not change my address. It's just you now have a new address on the post-it note. Yeah.
You do PA equal to 0, that should always work, right?
Yeah. I mean, you could say that PA is like const if you wanted to, and then it would complain, right? So if you say that PA is actually, int star const like this, then PA equals 0 is not allowed. And in fact, it didn't compile because that's not anymore allowed. So that was the question. All right. Okay. So this one, I think everyone has done in the lab last time. I want to do one more thing so that we kind of had a lecture at a correct place. We'll go back to talking about pointers a lot, obviously. So printf. So you've seen it being used. It's a little bit complicated, which is why we waited until now. So printf is what's called a variadic function. That means that it takes variable number of parameters. It's the same as print in Python. You can also give prints, different numbers of parameters. It's fine. So the way it works is it gets the format string and it prints the string. The way it does it is you tell it what type of data you want to give it. And it interprets the data that you give here as if it were whatever it is that you say here. So %d would be decimal, %c would be character, %s would be string, %ld would be long decimal. That means a 64-bit integer. So let's try to print this stuff and see what that does. So here it wasn't happy for obvious reasons, or maybe obvious reasons. So this is kind of interesting. So here we're saying print 87, so substitute 87 in here as a decimal, substitute 87 here as a character. And it just interprets the data in 87 as if it were a decimal number, as if it were a character. As it turns out, if you interpret 87 as a character, that's a capital W. I can also interpret it as an address, in which case it would be this address. So this is just a way of writing 57 in hexadecimal. So %p is pointer. This is where it crashed. Does anyone have an idea for why it would crash here? Yeah. Yeah, exactly. So what this is saying is, I'm giving you this thing, 87, and trust me, bro, that's the address of a character. And if it's not the case, so like what my poor computer is trying to do is it's trying to go to address 87 and get the character in address 87, but that's not even a valid address, so it crashed. Yeah. 0 is also not a valid address. You can say 0, it would also crash. Yeah. So 0 is also not a valid address. What would be a valid address? Like what does a valid address look like? Well, if I comment this out, so here I want to print address of X. So this value would be wherever this X is stored in decimal notation. Well, like we've seen lots of addresses, of course, right? So we already know what the answer would be. It's this, except in decimal. So if I print this, okay, so this now is an actual bona fide valid address. You can try to pretend it's a string, it's still not. So I don't recommend it. It's probably still going to crash, but that at least is not going to crash because it wasn't a valid address. All right, I will see you tomorrow. Thank you.